Hi, a little while ago, RS Components was kind enough to send me a Panel Pilot Ace panel meter display module. This is a fully programmable display panel that is able to read and write analog voltages as well as digital I/O and transform those into various display components on a panel which has got full touch capability, so that a user, for example, in some industrial or commercial application, could put very quickly up a control console for many different applications, including monitoring of plant equipment, maybe a power supply, heating and ventilation, some other control applications and things like that. So I've already put up one video which goes over the technical features of the panel meter, and what I'd like to do now is actually have a close look at the build of the meter. In future videos I'm going to put up a whole bunch of different sample applications for it, but for right now I'm going to basically have a teardown, see what's involved, what's built inside this thing, and also just give you a very quick demo of an application I put together in a few minutes to go with a power supply that I'm currently building. So anyway, without further ado, let's just get to the hardware. So this is the front of the Panel Pilot Ace, and as you can see, it's just basically a black panel with a 4.3-inch LCD touch screen display, and I haven't got it powered on right now, but what I will do is just flip it over so you can see what's on the back of this thing as well. So on the back of the panel, what we have is, it's all self-contained, but we have a USB input which you can use to program and also power the device, and at the bottom we also have a series of screw terminals where you can also power the device and provide analog inputs. The other the other connectors on the display that are all the way around the edge are used for various features of the display panel, including digital input and output, analog inputs, analog, or more specifically pulse width modulated outputs, and there are some future features that are also included on here which I'll link in the data sheets, or actually they're already linked in on the previous video, which include Ethernet, I2C, SPI, and various other features that have yet to be released. So these Panel Pilot Aces are very new on the market, and there's a lot of additional features planned for the future for these things that have not yet been released. That doesn't mean that it's not a capable meter in its own right. Even now it is, and it works very well, but there are some limitations that I've discovered in my initial look at this, which are not showstoppers. This meter, this panel display, is designed for industrial and commercial applications, but as it stands right now in its current configuration, all of the I/O, analog and digital, are connected directly to the microcontroller and the circuitry inside. So if you in typical industrial commercial applications, you may have things like 24-volt power supplies, 4 to 20 milliamp current loops, and things like that. And while this can actually take a 20 milliamp analog input, it does have common ground for all of the analog channels, and the digital inputs and outputs are all 3.3 volts. And as we look inside of this, you'll see why that is. And so if you were going to leverage this now for a industrial or commercial plant control situation, you would have to build some I/O devices to either isolate it from the system under test, or to at least drop the voltages down to ranges that were compatible with the device. Now the analog inputs, just to make this clear by the way, they are capable of going up to plus or minus 40 volts on their analog inputs, because it uses an ADC converter that has a preamplifier and divider network that is able to actually scale itself to suit the inputs that you're providing to it. The digital inputs and outputs, though, they are not. They're maximum 3.3 volts, which is due to the configuration with the microcontroller, and so you need to be careful how you interface those. You will need to have either transistor drivers or resistor divider networks, and potentially opto-isolators or something like that, so that you could hook them into plant equipment without running the risk of effectively damaging the controller due to transient spikes from the environment or something else. Anyway, that's enough chit chat for that. I actually, as I said, did do a previous video which details all of the specifications for this and a quick demo of some of the design tools. So what I'm going to do right now is whip the back off of this and let you see what's inside. The way you get into these meters, by the way, is on the edges of them. There's some little slots in here, and if you just gently put a probe in here, like a screwdriver or a plastic spatula or something, there are little tabs that you can just gently lever on to get them out. So if we just put this on the bench here, and we'll just get into this thing. As I say, you just gently push it in, and the back will just pop off. Nice and easy. And there we are. So we're in, like Flynn, as Dave Jones would say. So first thing we notice here is that it's just all a single board construction. We've got a great big CR2032 3-volt battery in the corner here. This is going to be for the onboard real-time clock. We have our connectors around the outside, a few surface mount components here. The circuitry here is the analog to digital conversion and programmable attenuator circuitry. And what we also have here is an SD card that, from what I understand, has got 2 gigs of storage and can be used for expansion and also storing your programs and everything that you upload to this. So I think what we need to do now is get a small screwdriver and take the panel out to have a look what's on the other side. Okay, found myself a small crosshead screwdriver, so let's just pull these out one at a time, just nice and carefully. So that's one. My bench, by the way, is anti-static, so just in case you're wondering, I don't want to damage this. And it's got a rubberized mat, so my display and everything else is protected from getting scratched and everything. So we just have 6 screws holding this board in place. Alright, so let's see what we have inside here. Just gently lift this up. So we've got the LCD connection on the other side of the board here that's holding this down. I just turn this around. And we also have this connection here, which is probably the touch panel connection. So we're going to have to deal with those so that we can get in here. So I think the first one to take off will be the touch panel. Just gently pull the levers forward. This is something that as a user you would not normally want to do, because you're probably going to invalidate your warranty for one, and also there is really no reason why you would need to do this. I'm just doing this really to kind of save you having to do it, because you'll see what's inside here without having to disassemble it yourself. And secondly, it'll make it a little easier for you. So now we've got the LCD display here, which is connected to this flex circuit and plugged in on this side of the board. It'll be a little bit interesting to get back in again, but nevertheless, you know, we just a couple of small tabs on the side and it should just drop off. There we go. So I'm not going to take the LCD out of here because it's basically molded into the case. So I'm not going to take it any further apart than that. As you can see, it's got a lot of the components for the LCD display are built right onto this flex circuit going around. And this one here will be the 4-wire resistive touch LCD touchscreen on the surface. So let's just move that out the way for a moment and we'll have a look at the board. So what we have here is, this is the LCD connection that we were looking at. We just pulled the wire off. We have some power management circuitry up here. Well, looks like we've got a resistor, 0.1 ohm, 100 milliohm resistor for probably measuring the current being consumed by the board. A little inductor and things, probably a little switch mode power supply, just to, because this is working from basically 5 to 24 volt DC input. So of course, you know, you don't want to be emitting a lot of heat while you take that down to the 3.3 volts for the controller, like the microprocessor. So this is a very efficient way of dropping those volts down. Now what I'm going to do right now is put the macro lens on my camera so that you guys can have a close look at what the things are we have on the board here. So we'll start off here with a nice close-up view of the Freescale microprocessor sitting there. And you can see it's a BGA device with all of the traces flying out from all sides to the different devices that are connected to it. And if we just scroll over a little bit, we'll have a look at this. So this is a inbound device. I'm not sure what kind it is right now, but I can see from the traces coming out of it, if you notice here, that it has pairs of wires coming out. So it's probably differential because they're trying to keep the length of the wires the same. That's why you typically see these snaking patterns going on. So if I just have a quick look up as what that device is, I'll get right back to you. Alright, so just did a quick Google on that, and that apparently is an 8 megabit, which is 8 banks by 16-bit wide DDR RAM chip. So that's obviously the memory, the RAM for the Freescale microprocessor. So that's pretty much all there is on this side that really warrants having a look at. If I just try and zoom out a little bit, as far as this macro lens will let me. And if we just check the rest of the board, as I said, we've already looked at this, had a quick discussion on that. It's just a standard switch mode power supply kind of circuitry. We've got the LCD, the connector, and everything else. So there's not really much else on that side that we need to worry about. So let's just flip this thing over and have a look at the devices that are on this side. Okay, so let's just put this down here. And what we have here, these are all near the analog inputs which come in on these terminals here. So if we just zoom in on those, see if we can identify what they are. Okay, we have this one here, which is a looks like a Texas Instruments MP222EC. So I'll have a quick look, or Intercell, sorry, MP222EC. So let's just have a quick look at what that is and let you know. So that MP222EC device is apparently a 3 to 5.5 volt multi-channel RS-232 line driver receiver. So that's for communicating with host controllers and things like that. Not the USB, by the way, but probably for some expansion or factory use of the board, maybe for setting it up and things like that. Anyway, so that's what that device is. Let's move on to the next one. The next device we come across is a programmable gain instrumentation amplifier, the PGA 280 from Texas Instruments. It's got a wide range input of plus or minus 15 volts at an 18 volt supply, and you can program the gain from 128 volts per volt to 1/8 of a volt per volt. So as you can tell from that, it will allow you to scale any input from just, sort of a volt or less, right up to sort of 30-40 volts coming in, down to a range that is suitable for the analog to digital converter. It's got low noise, near zero long-term drift, excellent linearity, 1.5 parts per million, excellent common mode rejection ratio, 140 dBs, differential signal output, overload detection, etc., etc. I'll link in the data sheet so that you can see more about that if you so desire, but that's what the board has for its 4 analog inputs. Let's see what this last device is for, which is just up a little bit. If we could just get it into view and try and get a closer view on it so that we can figure out what it is. So from what I can read there, it's a BR01, probably Burr Brown. It looks like it's a TI device. I'm just adjusting the light to see if I can get a better read of the text on it. Just trying on different angles. So I think the best, that's pretty much looks like a TI, and it's a BR01. So let's just go to Google and see what we can find out about that. So I'm not able to find out too much more about the chip without extensive research, and you'll be able to have a look at that yourself. Now, what I'm looking at here now is the digital I/O lines, which are basically along here on the edge connector that comes out on the pins. And as you can see with these traces, they actually go directly to the CPU, and the CPU runs at 3.3 volts. And that's why I was saying before that you're not able to connect any I/O on these pins that requires more than about 3.3 volts, and also, you know, it's not going to be able to drive too much current. Based on the ratings and the specifications, you're typically looking at a max of about 10 milliamps per pin for your input or your output. Sorry, for your output. So you need to be careful what you connect there. And also for your inputs, if you're using any 5-volt logic anywhere else, you'll need to have a level shift or at least an R, like a resistor divider network, before you feed it into the input of the chip, because you might damage the Freescale chip. And of course, you know, it being the heart of this whole display, you could easily damage that as well. Anyway, I think that's all the parts that are relevant for having a walkthrough on here. I think you'll agree. It's actually quite a nice, neat little board. I like the way they put it together. It's very well constructed. I don't see any suspect, you know, soldering or telltales of rework or anything like that, which is nice to see. It's well laid out. It's I think, as I said, the only criticism I would have is that this is aimed at industrial and commercial control systems and the likes, but it is using you know, direct to the CPU connections for its digital inputs and outputs, and even its analog input is still connected directly to chips that are sharing the same supply and everything else as the main processor. So you know, whatever you hook into this, you need to be aware of that, and you need to take appropriate protection for it, especially if you have long runs going out to any equipment that might be in the factory or on nearby workstations or something like that, you know, because any cables of a few feet long can easily pick up a lot of transient data and effectively damage the input to this Freescale processor or the A to D converter, although that is quite well protected by the analog front end programmable gain amplifier, as it's got quite a bit of circuitry built into it to protect its inputs, but it's not going to be you know, totally protected against high currents or high transient spikes or anything. Anyway, I think the next thing now is to assemble this back together and hook up a power supply and have a little play with it. So let's get that done. Okay, so here we are, all back together again. Let's just see if we can get this up and running. So make sure I haven't made any mistakes in the rewiring. Sorry, reassembly. Just give the display a wipe. It's got lots of grubby fingerprints on it now from being used, handled. So we'll just give that a clean. Alright, so what I have here, I'm going to move this out the way because I've got to put a USB connector into the back of it, is actually what I have is a the experiment board for this, so that it allows you to try it with analog inputs and outputs and things like that without having to actually put it into a panel. So let me just get that out and I'll just put this on and we'll give it a go. So this is the experimenter board. I had a quick review through it when we were doing the initial technical walkthrough of the board in a previous video, which I will put onto YouTube at the same time as this one. Just as a quick run through of what we have here is we have the digital inputs and outputs up here. You've got a row of LEDs and a row of switches that you can control the inputs and outputs. You also have 2 PWM outputs that you can use, 4 PWM outputs that you can use. These are connected to LEDs. They're only 0 to 256 resolution, so just an 8-bit PWM, so that's good enough for most applications. What you also have is alarm outputs, which are over here. There's one here and one here. They're separate digital outputs and they've got transistor assist, so you could drive a relay, a small relay or something like that with them, or you could just put an extra like a solid state relay or something like that if you wanted to connect something larger to that. Down on the left hand side here, this is an area where you could put the optional Ethernet module once it becomes available and you've got analog inputs on the side here. There's a few jumpers for all of these IOs that you can unplug to disconnect the switches and lights from it and enable you to directly connect devices on here. Remember inside when we were going through the walkthrough in the teardown, there was that RS-232 line driver. Well, that would connect to this module here, which you can connect to some device. And down in the bottom left here, we have 4 potentiometers that are connected, and you can actually use these to simulate analog inputs to the panel as well. So I've got a demo that I just put on here for testing my power supply before, and so I'm just going to power it up and show you what happens, or what it looks like. So just going to plug this in. Okay, so there we have it. I'm just going to power it up right now. Just plug in the other end into the USB port. There we go. So the lights just pop on and off very quickly. Display just resets itself and should come up. There's the Panel Pilot Ace logo, and I think I've got a splash screen or something on here as well as it powers up. Nope, this one comes straight up. Okay, so this is the little example I had before. So it's just got, if I just remember the right inputs. So this potentiometer here is measuring, but right now I've just connected to here. I actually had it connected to some real devices before, and I'll do that on a future video real soon. But as you can see, I can vary this input and it will measure the volts, and it's quite responsive, up to 5 volts. I mean, the inputs will actually go negative as well, but I haven't got that set up. I'm just going from midpoint up to 5. And of course the current inputs, this one here, again, the scale actually for this one is set a lot less, so as you can see it very rapidly goes up to 5 volts. Resolution is pretty good on these things. As I say, it's a 12-bit A to D converter, and they're all precision devices, so you can fairly well rely on the accuracy of it. We'll do an exact comparison with a DMM in a later video as well, but this whole display here with the logo and everything else is something I just put together over Christmas, hence the Christmassy feel with the little minion there, just to show some volts and current for a power supply project that I'm doing. Anyway, that basically completes the teardown. I just wanted to see and show you that the thing is still working after we've ripped it apart and put it back together again. I will have to set the clock, and I'll do that in another video. What I want to do is show you quickly how you can start now creating some panels of your own, both analog and digital, this one being a digital one. You can add your own logos and things like that to the design. It supports animated GIFs and things like that. As I said during the teardown, the thing you got to remember though is it is 3.3 volt TTL logic for all of the digital inputs and outputs. So be careful of what you put into it, and be careful of cable lengths and things that you use. Aside from that, that pretty much completes the teardown for this video. So hope you liked it, and we'll look forward to presenting you the next one where we start actually hooking it up to devices and things like that, and I'll show you some basic circuitry that you can construct on either on a breadboard to test it, but later on some more permanent prototyping board, like either Vera board, or if you can make a lot of them, then getting circuit boards made for them. But what I want to show you is controlling large relays, maybe sensing some temperatures, 4 to 20 milliamp current loops and things like that. Anyway, that's for the future video, so let me sign off now. As I say, hope you liked it. Give me a thumbs up or a like, depending on where you're watching this from, and we'll be back soon.